Okay, let's continue. So in the last class we essentially looked at the input referred noise and offset calculation in your 5 transistor op-amp, telescopic cascode and folded cascode. So that is all done. So after looking at all these cascodes, what did we see next in the course? After we looked at telescopic, folded cascode and all, what was the next thing we looked at? 5 trans to OTA cascodes. Then what did we see next? Huh? 2-stage op-amp. I mean, essentially we saw, what was the issue with single stage OTAs? We can't drive a small resistive load, so we decided to have a dedicated stage at the output for driving load. That gave rise to the multi-stage structure. So let's say I draw it using triangles like this. Let's say we consider a 2-stage OTA. And of course, now if you have multi-stage structure, what can go wrong if I put it in feedback? Stability. So you do some compensation. So let's say you might do some Miller compensation by putting some caps here and there, right? But for noise calculation, we will not consider capacitors. We will not consider the frequency dependence. For a quick calculation, we'll try to get an estimate of the low frequency noise alone, right? So for low frequencies, what can you say about the capacitors? Open. So we'll only look at low frequency noise part spectral density. If you want to get the exact frequency dependence of the output PSD, you simulate it and check. That's the best thing to do. Now in this 2-stage, you know how to model the noise of each of the 2 stages, right? You can model each of the noise with the input referred quantity. And if you assume that the input impedance of both stages is infinity, I just need the voltage source. So let us say you already computed the input referred noise for both stages, that is Vn11, let us say Vn in 2, let's say this has a gain of A1, A2. Now our goal is to try to model the overall noise here. Now the goal is to model the overall noise in this 2-stage structure using a single voltage source at the input. Right? So let's just call it N in total. So now you can directly tell me what will be the contribution of this Vn in 1 to this total Vn in. That's going to come directly, so I'll write it directly like this. So let us say Vn in total, this Vn in 1. Similarly, what will be the contribution of Vn in 2 to the final Vn in total? Divide by? No, if I look at the only voltage. By how do you say it's by A1?
If it's at the input of A1, after crossing it, it has to be equal to.
Yeah, so as he's saying, you can think of it in any ways. So I want to add some quantity here, which after getting amplified by A1 is as though I am adding an extra noise of Vn in 2. So that quantity has to be Vn in 2 by A1, right? Or you can actually do the same thing. You can find the total noise at the output divided by the overall gain from the input to the output. We have been looking at short circuit output current, but we can also find the noise in the open circuit voltage. So due to Vn in 2, what will be the noise at the output? How much of this will come at the output? A2 times Vn in 2. Now I want to refer this back to the input. So I'll divide this by what? Same thing, whichever way you want to do it, you can. Okay, so now this is 2-stage. So if let us say you go for a 3-stage structure, you can easily extend this argument. So let's say you have a 3rd stage having an input referred noise voltage of Vn in 3, having a gain of A3. So once again I wish to do the same thing. So how much of Vn in 3 will appear at the input? By? Make sense? I wish to add some quantity here, which after getting amplified by two gain stages should behave similar to Vn in 3. So essentially divided by A1 in. And this you can basically keep extending it. So the idea is the noise of the first stage is getting divided by the gain it sees. Second stage gain is getting divided by the gain it sees before, which is A1, A2. And in such a multi-stage structure, let us say in a multi-stage op-amp, the maximum gain is coming from which stage? First or first two stages. So how can I approximate this further as for all practical purposes? I have Vn in 1, Vn in 2 by A1, Vn in 3 by A1, A2. So how can I approximate it as? Just Vn in 1. Fine. That's all. So that's all. No need to go and compute because you've already done all the calculations for basic structures. Same thing. And this typically is the case whenever you have a long chain like this, where each stage of the chain is providing you some gain. Typically, the noise of the first stage is the dominant one. So the first stage is typically designed to add as low noise as possible. Cool. So any questions on this? I guess this is simple enough for you to easily comprehend. No doubts, I hope. And I mean, although I looked at for noise here, even if you try to calculate the input referred noise, the same result will hold. Right? Again, the offset of each stage you can model it using an input referred quantity. Once again, if you model the overall input referred noise, the same result will extend. So that's about multi-stage structures, noise in multi-stage structure and offset. So after looking at multi-stage op-amps, what did we see next in the course? We looked at fully differential structures because, as we saw, if you have a single-ended structure, it is a single-ended line. It is very susceptible to any kind of common mode noise, like noise in ground, noise in supply, or any interference. So that's why we decided to go with a fully differential signal like this. So let's look at noise in a fully differential circuits. And I'll just draw a generic block of a fully differential circuit. So let us say I have one half circuit like this. I have another half circuit like this. Let us say you apply the positive input here, the negative input here, and let's say you take the outputs here. Let's call this the output plus, the output minus. And now if I connect this to ground, this is not a fully differential structure. This is pseudo differential. Oops. So what should I change here to make it a fully differential? Did you get the question? Hold on. Yeah, what I'm saying is if I have two isolated structures like this and then apply inputs and take the outputs, this is not a fully differential structure, right? So what should I do to make it fully differential? You add a tail current source or something to give common mode rejection. So let's say you add something here. So let's say something is added. Okay. Now of course you need to have common mode feedback for this structure. And again I'll draw it at a block level. Let us say you sense the common mode using something. And then you have something that goes and sets the common mode for the it's a very block level representation. And if you look at the CMFBs that I have drawn it in blue, you can notice that this part of the CMFB is common to both half circuits, whereas the common mode detecting part is individual, right? So if you were to even break it down and draw at a more simpler level, you can consider a fully differential system to look like this. I have two half circuits, or I'll directly draw it here. So I have two half circuits. You apply Vi plus, Vi minus, and then you take the outputs here. Now I have some portion of this that is common to, and some network I have which is common to both the circuits, right? I'll call this the common part of the circuit. This includes some part of your common mode feedback, all tail current source you have, etc. Fine. at a very generic level, I can model it this way. Oops, sorry. Fine. So now let's try to find the noise in this. Again, let's look at a general result. So again, to find the noise, assuming that the input impedance of the circuit is infinity, you just need an effective input referred noise voltage. So for finding the input referred noise voltage, what is the value of the source resistance we use? 0. So that means the input is basically shorted. And the same procedure, I will find the total noise in the output, either in the short circuit output current or in open circuit voltage. Here I look at the voltage because that's easy to see here. And then I'll divide it by the overall transfer function from input to output. So let's break it down into multiple pieces. First, let's consider the noise in the common part of the circuit, and then look at the noise in the half circuits. So let us say there is some noise generated by this common part of the circuit. That noise will be injected in both the halves. How will this noise get split in the two half circuits? Equally or with difference? It will get divided equally, because both are identical half circuits. It will get divided equally. Then what can you say about the voltage generated here due to this noise? They will be equal. We are only interested in the difference between them. So if I take the difference, what can you say about the noise? That gets completely cancelled, so you don't have noise from this common part, right? So I'll directly write this. There is zero noise coming from the common part of your circuit. Again, that should make sense because this is a fully differential system. It will only respond to differential signals. So any common mode noise or common mode disturbance that is getting injected will be properly rejected by the system. So that does half the job. So now let's only look at the noise in the half circuits individually. Let me erase this. Okay, yeah. So let me mark it here. NC adds no noise. Now let's consider the noise sources in the half circuits. So let us say in the half circuit here I consider a MOSFET, and let us say the noise of that MOSFET I model it using an input referred noise voltage with, let us say, call it VNK plus, because it is in the positive side. Similarly here I'll have another noise, similar MOSFET. I'll model that noise also using a voltage source. I'll call that VNK minus, because it is in the negative half. So now tell me, I have a fully differential system like this. I have two inputs. I need to find the output voltages. What is the best way to solve? Superposition you can do for any linear network, but on top of the fact that this network is small signal linear, I also know that this is a symmetric network and differential like this. So what can I do? I can look at half circuit. So as usual I'll consider half circuits. So let us say I'll decompose as half circuit VNK common, which is average of the two. Similarly I look at a differential part, which is VNK plus minus VNK minus. So which means now the individual signals I can write it like this. VNK plus is the common part plus half the differential part, and the negative side is VNKC minus half the differential part. Fine. And yeah, even before we proceed further, this is the noise of a MOSFET, and let us say the MOSFET has a transconductance GMK, kth MOSFET. What can you say about the path spectral density of this noise? The voltage path spectral density for MOSFET, what is it? 4 kT gamma by GMK. Similarly, if I look at this noise here, that is also coming from an identical MOSFET with the same GM. What can you say about the path spectral density of this noise? Same, right? So Vnk minus of f. So I'll call this directly as Vnk of f. That's all. And please note that just because the path spectral densities of the two signals are equal, the signals themselves are not equal. It is just that one property of the signals are equal, and that property turns out to be the path spectral density. But if I look at Vnk plus and Vnk minus, they are again uncorrelated, because they are coming from two different MOSFETs. The noise mechanism in the first MOSFET and the noise mechanism in the second MOSFET, they have no relation. So they are nicely uncorrelated like this. Cool. So now let's continue the calculation. Okay, so now let's first calculate the contribution due to the common part. So which means now I am considering VNKC and VNKC on both sides. I have the same signal applied in both half circuits. What can you say about VO plus VO minus? They will be same if I take the difference. Okay. So again, same argument. Any common disturbances will not result in a differential noise in the signal. Okay. Is there any confusion on this? Okay, so now let's look at the differential part. So I'll erase this. So if I look at the differential part, what I am saying is this: in one half I have plus Vnkd by 2. In the other half I have minus Vnkd by 2. So again, this is a symmetric circuit. I am providing an anti-symmetric excitation. What can you do to solve and simplify? Yeah, again, we can use the fact that all the nodes along the line of symmetry will be 0. So you can reduce it to a differential mode half circuit. So you can just consider the differential mode half circuit. So let me try to draw it here itself. If I can reduce this. So you look at, let's say, one half circuit. That's it. And you consider, let us say, Vnkd by 2. So this is the differential mode half circuit that you are considering. Okay, so now we can find VO plus might be some alpha k times Vnkd by 2. Find some transfer function, linear transfer function. Similarly, what can you say about VO minus? Minus of that, minus alpha k. So my total differential output will be 2 alpha k, I mean Vnkd by 2, which is fine. And this is only the contribution due to the kth noise source. Now to find the total noise, I will do it for all noise sources. So my total output noise will be summation of this. Done. Now this is the effective noise you find at the output, differential output. Now I want to calculate the input referred noise. So what will I do now? Divided by, differential mode gain or common mode gain? Differential mode gain. So to find the input referred noise, I'll basically take this entire thing, summation k alpha k Vnkd, I divide it by the differential mode. That's all. Let me make some space here. So that's all, we have computed it. Let's try to write the path spectral density now. So now tell me what is SVN in of f. I have square of the gain, which is 1 by the differential mode gain square, summation k alpha k square times the part spectral density of the differential noise, right? And this is the differential noise, Vnk plus minus Vnk minus. What is the part spectral density of the difference between these two? 0. Why? Remember that the signals, they are not equal. I mean, I can say I have two signals having the same average, but doesn't mean the two signals are equal, right? It's the same thing, right? I can have a signal which is always 0. I can have a sinusoid whose average is 0. All I know is the average of the signals is same. Similarly, here the part spectral densities are same, but the signals themselves are not equal. They are uncorrelated. So what will be the part spectral density if they are uncorrelated? Sum of their part spectral densities. Okay. And both their part spectral densities are same. So this simply becomes 2 times SVnk of it. Is it clear? Because remember, the noise voltages here, they are uncorrelated. So if I take a difference, or if I take the summation, because they are uncorrelated, you can add their powers and part spectral density directly. Okay. So this I can rewrite like this. It is twice 1 by the differential gain square summation k alpha k square SVnk of f. And this you can actually think of it this way. But till this point, is the result clear? So if there is any confusion in this, let me know. I'll clarify it now itself. Okay, trusting that this is clear, let's try to make sense of this. See here, this SVnk of f is essentially the part spectral density of the noise source in one of the half circuits. Fine. So what you have essentially done here is find the transfer function from that noise source to the output divided by the differential mode gain square, and then you take twice of that. So in a way, this effectively is the input referred noise of your half circuit, right? Because what is this? This is the part spectral density of the noise source in one half circuit, and then you find the transfer function of that noise source to the output, that is alpha k, and then divided by the differential mode gain square, right? So the final result is this. It's pretty simple. If you have a fully differential circuit, to find the input referred noise part spectral density, you construct the differential mode half circuit, right? And then find the input referred noise of this differential mode half circuit. So let me call this SVN tilde of f. Once you know the part spectral density of the differential mode half circuit, you multiply this by 2. That gives the input referred part spectral density of the fully differential circuit. That's all. Is it okay? At least very qualitatively it should make sense, because in the fully differential thing I have two half circuits. The two half circuits are uncorrelated. So if I know the input referred noise PSD of one of the half circuits, for the overall fully differential case, it's going to be 2 times of that. But this is a more formal way of actually proving it. So which means even fully differential circuits are now cakewalk for you. If I give a big fully differential circuit, we can reduce it to 1/2 of the circuit, and we have already computed noise for half circuits, single-ended stages. The same calculation. So I will not do any calculation because we have done some of them. It's the same thing, nothing changes. So you just take the differential mode half circuit, find its input referred noise PSD, multiply it by 2. That's all. Okay. Cool. So at this point, again, you should be asking a question. So as usual, I'll ask it myself. So it looks like the noise in my fully differential circuit seems to be 2 times more than in my half circuit. So the natural question to ask is my fully differential circuit poor in terms of noise performance? Seems like a natural question to ponder. To answer that, let's actually look at it in detail. So let's say I take this side, I take a single-ended case. Here I take a fully differential case. I know that for the single-ended half circuit, if the path spectral density, when you refer to the input is some SVNN, what is the path spectral density in the fully differential case? 2 times that. So if I know the path spectral density, how will I find the total noise power? Integrated. So let us say you integrate this, you get some sigma square n. So here what will be the noise you get? Noise power? Huh? I mean, I integrate this thing, I get some sigma square. I integrate this thing, what will I get? So looks like the noise power is 2x, but it turns out in practice we are actually not worried about the absolute noise power. What actually matters is signal to noise ratio. Simply because let us say you can have one system where let us say the noise is some 10 microvolt square noise power. Another system can have noise power of 100 microvolt square. But this doesn't matter because let us say the maximum signal power the first system can handle is only say some 50 microvolt square. Then you see that my signal power and noise power are very close. I will not be able to differentiate what is signal and what is noise. Whereas in the second system, if this can take signal power of 1 millivolt square, this is significantly better. So that's why absolute noise power makes no sense. You look at how much noise is added with respect to my signal. So let's quickly compute what will be the SNR in both cases. I'm hoping SNR is a term which is not, I'm hoping you're not hearing this term for the first time. Signal to noise ratio. You have heard this before, I hope. Fine. So let's calculate signal to noise ratio. So in a single-ended case, let us say the supply is from 0 to VDD. What is the maximum sinusoid you can apply here? Amplitude. VDD by 2, the signal has to be centered around this. Amplitude is VDD by 2. So what is the maximum signal power you can have in the system? No, VDD by 2 whole square by 2. Correct? VDD square by 8. So if I find the maximum sinusoidal signal to noise ratio, that is some VDD square by 8 sigma square n. I just found the maximum signal power and divided by the noise power, which is sigma square. Now let's look at the fully differential case. So even in the fully differential system, the supply is from 0 to VDD, right? But unlike a single-ended case, here the output or the input is not a single signal. It is difference between two complementary signals. So which means if let us say the positive side the signal does this, on the other negative half the signal will actually, correct? So my actual signal is now the difference between these two. So if I take the difference, what is the sinusoidal amplitude I can have? Yeah, which is what? Right? So what is the maximum signal power I can have here? VDD square by 2. Is that clear? Oh, I mean, if a signal, I mean, if a sinusoid has an amplitude of A, what is the power in the sinusoid? I mean, here the maximum amplitude you can have is VDD, right? That's clear, right? So now we can find the maximum sinusoidal signal to noise ratio. That's going to be VDD square by 4 times sigma square. So now tell me which is better, single-ended or fully differential? Fully differential, right? Because the SNR you can get here is 2 times higher than what you can get in single-ended case. But anytime you get something good, I mean, don't take it as it is. You understand what is the catch here. I mean, someone gives free chocolate, don't take it, right? I mean, you see what is the catch. Same thing here, you are getting higher SNR, but let's see if we are getting it for free or we are losing or we are paying some price for it. So now tell me, is there something that we are losing when we do this? Remember, if I have a single-ended structure, if the DC power consumption is some PDC, here I have fully differential case, but I have two of them operating. So the DC power consumption will be. So it is not like we are getting this SNR advantage for free. We are burning twice the amount of power. That's why even the SNR is twice higher. And in fact, this is a fundamental trade-off, that you can actually burn more and more power to reduce noise in your circuit and increase SNR. So what that means is this. So let us say you have some circuit. This can be single-ended, fully differential, doesn't matter, something. Okay. So let us say this is realizing a transfer function h of s, having some internal nodes like this. I just marked 4 nodes for example. And let's say the noise power here is some sigma square n. Now let us say you want to maintain the same transfer function, but just reduce the noise in the circuit by 2x. So it turns out one brute force way is this. You have an identical copy of the same network, okay, and you feed in the same input to both of them. If I feed in the same input, what can you say about the outputs? They will be same, so I can short them. And what can you say about the corresponding internal nodes in both the circuits? I mean, what can you say about the node voltages in both the circuits? If I see two nodes with the same potential, what will I do? I'll go and short them. So I can essentially go and do this. If I do this, if it's clear that the transfer function is not changing, right? But the moment I connect the nodes this way, in my original circuit, if I had a resistor R, after doing this connection, what is effective resistance I'll have? Similarly, if I have an L inductor, C becomes, if I have a GM, how much it will become? So now we already know that the power spectral density, the voltage power spectral density, it all depends on 4 kT R or 4 kT gamma by GM. So now tell me, if I do this way, what will happen to the power spectral density? It goes down by a factor of 2, which means what can you say about the noise power? That also reduces, because transfer function is same. I am only changing the low frequency power spectral density. So which means the noise power also scales down by a factor of 2. This will become half sigma square of. So in general, let us say you have some circuit, and let us say you want to reduce the noise in the circuit by a factor k. What this says is, all you need to do is the following: take all resistors in your circuit, make it R by k, all inductors you scale it by a factor of k, all capacitors you make k times C, all GMs you make it k times G. If you do this, the transfer function will remain exactly the same, but the noise power will reduce by a factor of k. But what can you comment about the power dissipation in the circuit now? Yeah, because it is as though you are putting k networks in parallel, the power consumption increases by a factor of k. So here the noise power reduces by 2, but power dissipation increases. And again, remember, this k need not be an integer, it can be any real number. Let us say you want to reduce the noise by 30%, we can make k to be 1.3, so we can do the same thing. And this can also work in the opposite way. So let us say you have designed some circuit where the noise is really small, but the power consumption is very high. So let us say you are okay with having a higher noise, but you want to reduce the power consumption. You can do the ulta, you can choose k to be less than 1, and you can actually reduce the power consumption at the cost of increased noise. Is this clear? So this is often referred to as noise or impedance scaling. Cool. So now tell me, if I say that I have some two circuits, let us say I say circuit 1 has a higher signal to noise ratio than circuit 2. So would you directly comment that circuit 1 is better than circuit 2? Why not? Yeah, because you already know to reduce the noise power or to increase the SNR, I can go and burn more and more power in my circuit, because as you know, SNR is directly proportional to power dissipation. Right? Similarly, if someone claims that, hey, my circuit consumes 10 times smaller power than another circuit, we cannot directly say that this is better, because if you reduce the power consumption, we know you'll have higher noise power and lower SNR. So if that is the situation, what might be a reasonable metric to use for comparing circuits? I cannot only take SNR, I cannot only look at power consumption in isolation. What should I do? I take the ratio of them. So you can do either way. Typically you can take SNR by power consumption. This will be a good metric to judge, right? Because if this ratio is large, which means you are getting a higher SNR but with a smaller power consumption. And this typically is one of the metrics that is used for comparing circuits, or especially analog circuits. So this is what we call as figure of merit, or FOM. It is just a metric that we use for comparing multiple analog circuits. And it turns out in practice, getting a higher SNR with a lower power consumption is much easier to do for a lower bandwidth than to do for a higher bandwidth. So even better comparison metric is taking the product with the bandwidth. Because if you want to have a larger bandwidth, you need to have more and more GM. So the power consumption automatically will increase. So to have a good comparison, this is what we typically do. Okay. Cool. So any questions on this? The key takeaway I want you to have is this: if you want to systematically reduce the noise in your circuit without touching anything, just take all the impedances in your circuit and scale it. That's it. And you can work the other way if you can reverse scale it to reduce the power consumption at the cost of noise. So the figure of merit we typically have is this: look at the ratio of SNR by power consumption and multiply by bandwidth. Cool. So now that we are in the discussion of scaling, let's look at another scaling that you might want to do in practice. So let us say you have some circuit that is realizing some transfer function h of s, and let us say if I look at the sinusoidal frequency response, that is if I look at magnitude of h of f, let us say it looks something like this. Now let us say the goal is to scale the bandwidth of the circuit by a factor of 2. That is, let us say here, let us say the bandwidth was some f0. I want to have a transfer function that looks like this. It is the same thing, but the bandwidth has become f0 bit. Or you can the opposite also. You want to increase the bandwidth, right? Same thing. So let's see what might be a decent way to do this. So first of all, tell me, if let us say earlier the transfer for this frequency response, the transfer function was h of s. If I reduce the bandwidth, what can you say about the modified transfer function? So when I say that the bandwidth is reducing by a factor of 2, the function has expanded or function has shrunk. If a signal has shrunk in one domain, So how do you say? 2s. Fine. Fine. So now all you need to do is the following. If you had a transfer function h of s, you want to make sure the transfer function realized is h of 2s. Right? Now can you like think and tell me how can you scale s by 2 times s? I mean the idea is in my transfer function I have s times something blah blah blah, right? Which means wherever I have s, now it should be 2 times s. So what can you do in your circuit to get this happen? Yeah, that is invariably that, but let us say in my circuit I have, let us say, transconductance, resistors, inductors and capacitors. What will you do? Yeah, why? Yeah, see, what he's saying is this. I mean, let us say you have your transfer function. There is going to be an s term, right? Now this s term is coming because of what kind of circuit elements? Inductors and capacitors. So we'll either have s times c or s times ck or s times lk. Now if I want to scale s by 2 times, what can I do? I cannot just do only for c. I should also do for l. Right? I'll take all the capacitors and all the inductors in my circuit, scale it by a factor of 2. That essentially will do this. So that is one thing you can do. So you take all inductors and capacitors, scale it by a factor of 2. Make sense? No, but remember your transfer function is a unitless quantity. So in your transfer function you will not just have s times c, right? It will have s times c times something, correct? And what will that other term be? I mean, is the argument clear? Let me see if I can. So, okay, let me erase and write it here. Okay. So what I'm saying is your transfer function is a unitless quantity. So you cannot have a term s times c in your transfer function, right? Because s times c has units of what? What is the unit of sc? Conductance. So you will not have sc, you will have sc times something. What will be that term? Some r, right? Might be some, let us say rk, or it could be a transconductor. So you can have sc by gm, right? sck by gmk. Same thing with the inductor, you will have slk by rk, or you will have slk times gmk. Correct? So now tell me, if I don't want to touch the reactive elements, what is the other thing I can do to accomplish the same task? Huh? I'll take all the resistors and make it what? Rk becomes 2 times Rk. And what about the transconductances? Oh sorry, SLK, yeah, correct. Did I make a mistake? Huh? I don't understand. SLK?
That might not work for SLK. At that time, it will be SLK by 2.
Did I make a mistake? Okay, fine. So sorry. Yeah. Fine, let's only look at this. Okay, let's see if this becomes SLK into GMK. Yeah. Okay, first let's only look at this factor. Okay, if you scale this. Yeah, you are right. So let us say you have, I'll make it better. Let's say there is no inductors, for example. If it's inductors, it is becoming messy. So let's only consider caps now. So then what can you do? Yeah, I can make Rk to be and GMK to be Let's ignore inductors. So you can do either of them, but of course each of them will have its own, pros and cons. So let's just see what will happen in both cases. Okay, fine. Yeah, tell me, if I only scale the capacitors in the circuit, what can you say about the low frequency power spectral density? If I look at the low frequency power spectral density in my circuit, earlier, maybe I'll sketch it. Let us say earlier the power spectral density was looking like this. Now I have scaled only the capacitors. How do you think this function will change power spectral density? Okay, bandwidth is going to scale down, but what can you say about the low frequency portion? Will it change or will it not change? Same? Why? What is deciding the low frequency power spectral density? Resistors and transconductors. You have not changed the resistors or transconductors, so the low frequency part is going to be same. So this essentially will become something like this. It just scales down. So earlier, let us say this had a noise power of some sigma square. What will be the noise power in this new transfer function now? Same. How will you find the noise power from the power spectral density? You integrate this entire thing. The white curve, when I integrate it, let us say I had some sigma square. Now the bandwidth has become smaller. So if I integrate this, how much will this be? Reduced by factor of 4. 4. Why? I hear 2 and 4. What is correct? Okay, let's take a simple case. You had, let us say, this was the first case. What was this area? Let us say this is A and B. What is the area? A times B. Now what have I done? Have I changed the, did I change the vertical portion or horizontal portion? Horizontal portion has become B by 2. What is the area? So what do you think will happen to the noise now? Okay. So here the noise will go by a factor of 2. So what can you say about SNR? Increase it by a factor of 2. So let us say now I consider this case where I am scaling the resistances and transconductance. Then how will the power spectral density look like? Bandwidth is of course reduced by a factor of 2. But what can you say about the low frequency power spectral density? It has become become twice or reduced by a factor of 2. It has become twice because it's 4 kT times R or 4 kT by GM. So this will actually become 2 times. So let's say it will do this, and then it will. So now what can you say about the area of this curve roughly? It's going to be same because x-axis also shrunk by a factor of 2. In the other axis also it has increased. This will be same. So here SNR is same. So now tell me, doing which is better? Scaling the reactances is better or conductances is better? Okay, again, oops. Why do you say scaling reactances is better? Or simple, left side is better or right side is better? Why? But are we getting this for free or something else is happening? Why is power increased? In the left side, I am only scaling the capacitances. So the DC power consumption, will it change or will it not change? DC power consumption is still the same. Here what I have done, let me write it here, PDC is same. In the right side I am increasing the resistors, reducing the transconductances. What can you say about the power consumption? It's reduced by a factor of 2. So here again PDC has reduced by a factor of 2. So of course you reduce the power consumption, SNR will also degrade, right? That's all. So it is not like you are getting anything for free. Once again, it is the same fundamental noise and power trade-off. Here the power consumption was the same, or I would say compared to the right side case, the left side case consumes 2 times more power, so it also has 2 times higher SM. It's not like this is having 2 times higher S0 for free. That is happening because compared to the left side, the power consumption is 2 times higher. So this is sometimes called bandwidth scaling. Cool. So I'll stop here. We'll see today evening 6:35 in the same room.